The parameter count in deep convolutional neural networks, DCNNs, quickly grows. It's a common challenge faced in the world of artificial intelligence. In DCNNs, the number of parameters in pointwise convolutions rapidly inflates due to the multiplication of the filters and input channels from the preceding layer. This multiplication effect can lead to a dramatic increase in the total parameter count. Now, why is this a problem? This parameter explosion can create significant hurdles, including increased computational complexity and decreased efficiency. In simpler terms, it's like trying to juggle too many balls at once. The more parameters there are, the more difficult it becomes to train them all effectively, and the more computational resources are required. The question then becomes, how can we tackle this parameter growth without degrading the learning capability of DCNNs? Well, stick around as we dive into a solution to this problem. Enter grouped pointwise convolutions, a technique designed to make pointwise convolutions more parameter efficient. This approach leverages the power of parallel branching. Picture a tree with multiple branches. Each branch represents a group of filters processing a fraction of the input channels independently. But here's the twist. Instead of letting these branches independent, we interleave the filter's output from separate branches at intermediate layers of successive pointwise convolutions. Imagine weaving together the branches of our tree, creating a stronger, more efficient structure. This intricate dance ensures that the learning capability of deep convolutional neural networks remains intact, while substantially reducing the parameter count. In essence, this technique is all about achieving more with less, optimizing the use of resources without compromising the learning capacity of the network. So, how does this technique hold up in practice? It turns out, grouped pointwise convolutions can significantly reduce the number of parameters in pointwise convolutions without sacrificing any learning capacity. When applied to various state-of-the-art deep convolutional neural networks, or DCNNs for short, such as EfficientNet, DenseNet-BC L100, MobileNet, and MobileNet v3 Large, the results were quite impressive. Let's take EfficientNet for example. The optimized version of it, dubbed CefNet-B032HH, saved a whopping 74% of the trainable parameters and 55% of the floating point computations compared to its baseline. Even more exciting, this reduction didn't come at the cost of accuracy. In fact, when trained from scratch, the optimized architecture achieved slightly higher classification accuracy than the baseline on the Cypher-10 dataset. Similar results were observed on the Cropped-PlantDoc and Oxford-IIIT Pet datasets. In the end, it seems that we can indeed make DCNNs more efficient without losing any of their learning capabilities. The source code is free. This is a truly useful technique that you can take advantage of it right now. Links to the paper and to the source code are listed in the description.